Okay, so what did we say yesterday about, name the kinematic quantities, just throw them out there that we talked about yesterday while I'm taking roll. What does kinematics mean? Study of motion. Motion without regard to the cause of the motion, just the motion itself. Okay, we haven't really gotten to what causes all this motion yet. That comes next. Let's see. Is Gabby here? No. Okay. Right. Who are we missing? Oh, and Lily. Okay. All right. So kinematics just studies the motion. What are some quantities that we need to add to our list of kinematic quantities? So everybody close up your Chromebooks for a second here. Throw them out there. What are some things we got to know? I'll start you off. Time, right? Time is a kinematic quantity. What else?
Meters.
Okay, meters are a unit of what? Of distance. Okay, distance. So distance is loosely related to what other quantity? Displacement or okay, magnitude. Well, that's a word we'll throw out too. To displacement or position, right? So if we're talking about being able to look at the motion of an object, we have to be able to pinpoint where it is, right? We call that its position. Position has to be measured relative to something. Usually for us, we pick the surface of the earth. That makes a lot of sense, but it doesn't have to be that, right? It could be if you were on a boat, for example, that was steaming across the ocean, you'd probably choose your reference frame to be the boat, right? When you talked about you went for a run, you don't really care about where you ran relative to some fixed point on the ocean. You care about if you're running around the big cruise ship. You're running around the surface of the boat, right? So it doesn't have to necessarily be the earth. It could be other things. If you're on a plane, for example, if you get up and you're going to walk to the bathroom on a plane, well, you're technically, relative to the surface of the earth, you're moving at several hundred miles per hour, but if somebody asked you how fast you think you walked, you probably would have just said, oh, about a meter per second, or 2 meters per second, or something like that, right? Relative to the plane itself. Okay, so position is a vector quantity. What are the characteristics of any vector quantity? It has to have two things. What's one of them? Direction's one, and then magnitude. So the magnitude's the number part. The direction is what it claims. It's the direction. Okay, while we're on the subject of vectors, so position tells us where something is at a given time, right? What's displacement?
Change in position.
Change in position, right? It's a change in position. If I move from this position to this position, well, my displacement is the vector starting here and ending here, right? Make sense? Okay, so how is that different then? How is displacement different from, say, distance traveled? Which is usually when we say distance, what we're talking about.
Distance traveled doesn't show a direction.
Doesn't show which direction. It's without regard to direction. But also, if you go out and you run 4 miles on a track, where it's a number, good. So the 4 miles tells you how much wear and tear to put on your shoes, right? I mean, how much distance did you travel with respect to the track, right? What's your displacement maybe after running 4 miles on a track? 0, because you're ending up, you have 16 laps, right? You end up at the same place you started, and so your displacement's 0, okay? What if I were to run, I gotta put a track up here. We'll use track a little bit. So here's my oval track, right? If I run 200 meters, I'm gonna start there and end there. Okay? What's the magnitude of my displacement at that point? Is it 200 meters?
No.
It's not, is it? Right. It's not. The magnitude of my displacement is that distance. Okay? Does that make sense? What's the distance traveled? 200 meters. Okay, so that's different. The distance traveled is going to be right here. what's my distance from the starting place, from the starting point? That, isn't it? Okay. So this is my distance from where I started. How is the distance from where I started related to the magnitude of displacement? They're the same, aren't they? Okay. Does that make sense? So the distance, now what if let's say that we're going to consider, let's do something different. Okay, so now we're just going to be on a straightaway. I'll take my example up here at the front of the room. So if I start here, let's call this 0. If I start here and I walk out 2 meters and I walk back 1 meter, my distance traveled is 3 meters, right? My displacement is positive 1. Agreed? What's the magnitude of my displacement? 1. So my distance from the starting place is 1, right? Let's try this again. Let's start here this time. So we'll call this 0. I'm going to go back 2, turn around and go forward 1. Okay? What's the magnitude of my displacement? Okay, the magnitude is 1. Yeah, that's what I wanted to get at. The magnitude is going to be the positive number, right? So the displacement is -1. The direction is negative in this case, isn't it? Right? But still, the magnitude of my displacement always corresponds to my distance from where I started. Distance is always going to be a positive number. Okay? Make sense? Okay, good. Okay, we talked a little bit about, probably the last thing, we talked a little bit about how we could, we talked about average quantities a lot in algebra-based physics class, right? So what is, from displacement, we went on to, position and displacement, we moved up one rung, maybe a little more complex, and we talked about speed and velocity and stuff like that. So what's the definition of average velocity? Displacement over time, right. Okay, so is it a vector quantity or a scalar quantity? It's a vector quantity, isn't it? Right, because displacement's a vector quantity. Okay, good. How is that different from average speed? Okay, so average speed is distance traveled over time, right? Okay, so once again, I could travel around. Let's say it takes me, so I'm driving in a car, and it takes me 10 seconds to go 400 meters around this track. What's my average speed? 40 meters per second, right? 400 meters divided by 10 seconds is 400 meters per second. Notice the units of speed or velocity, they're built from our standard SI or MKS units, right? They're built from meters and seconds. It makes sense that if speed or velocity is measuring units of distance over units of time, we would expect the standard units to be meters per second, right? Okay? What's my average velocity? 0. Right? Because my total displacement is 0, right? Divided by 40 seconds is that what I said? 10 seconds is 0, right? Okay. Okay, what about instantaneous? We talked a little bit about that too, right? So average velocity is defined as displacement over time. Average speed is distance traveled over time. And a lot of times that's pretty useful to us, especially if I think the example we used yesterday is if we want to plan a trip and we know what our average speed, we can estimate what our average speed is going to be as we travel. That's a useful thing to know because it helps us predict how long it's going to take to get someplace a long ways away, right? Okay, but a police officer is more interested in your instantaneous speed than your average speed. So that's something we need to talk about too. What was our strategy? This was kind of interesting. What was our strategy for getting at an instantaneous speed or velocity? Yeah. Small intervals, right? We're going to take very, very small intervals of an average, right? So, and when you get into calculus, you start to talk about ways that you can make that a perfect representation of an instantaneous quantity by taking what we call in calculus the limit of the quantity, speed or velocity, as that increment approaches 0. right? And then it gets infinitesimally small, and we get infinitely precise with our measurement, right? A speedometer does something kind of like that, actually. It's really small. It averages out really small intervals of speed measurements, okay? Or it can, not at all. Okay, we're good? All right, next step. Next step in the process. So let's make our list of kinematic quantities. These are the ones we've already talked about. And let's divide these up into two columns. We're going to have a vector column and a scalar column, right? So we said the vector position, and for now, we'll just call that x, with a vector hat, right? Because we're only moving in a line for now. Good. Corresponds to what scalar, do you think? It's going to be a little strange, but this one is, we wouldn't use this often, but that would just be distance. Right? Does that make sense? Just distance from some reference point. Okay? We talked about displacement. And we call that delta x, right? Delta means change in. We could define that as displacement equals the final position minus the initial position, right? And that's sort of the scalar analog of that would be what? Displacement. They're not identical, but they get at the same thing. Distance traveled. That's kind of like, sort of like delta x, right? Okay. We talked about velocity. I'm going to call it average velocity. Average velocity. So average velocity, when we have an average quantity in physics, we denote an average by putting a bar over the top. That means average. And then I'm going to put a vector hat there too, because this is a vector quantity. So what's average velocity equal to?
Average speed.
Let me say it wasn't a definition of average velocity, though. No. Average velocity is just displacement over time. There you go. So it's going to be change in position or displacement over change in time. And if we start at time 0, delta t is just the same thing as t, isn't it? The amount of time it took. Does that make sense? Okay, so there's average velocity. And then that would correspond to, of course, average speed would be the scalar analog, right? And instantaneous velocity, we could just call v without a bar. Okay. And the scalar analog would be instantaneous speed. I'm going to get lazy. Sometimes when I say velocity, I'm probably going to mean average velocity. If we get we're talking a lot about average velocity, we'll probably just say velocity. But the context will indicate whether or not we're talking about an average or an instantaneous velocity. Okay? All right, so what do you suppose is next then? We went from position to velocity, which is measuring change in position. What do you think the next step would be?
Acceleration.
Acceleration, which measures what? Velocity. Okay. So the next thing we'll add here is average acceleration. And so we're going to call that A bar. We'll almost never talk about instantaneous acceleration. So most of the time we'll just leave the bar off and just know that if we say A vector acceleration, we mean average acceleration. So what do you suppose the definition of that is? Now, there's an interesting relationship here. It's kind of like an analogy. The relationship, think about it this way. Velocity is to position as acceleration is to velocity. Okay? Acceleration is related to velocity in exactly the same way that velocity is related to position, right? So acceleration then probably equals what? If we define average velocity as the change in position over change in time, change in velocity over change in time. There you go. Okay, make sense? And what's the scalar analog of that? Acceleration. We don't have another name for it, it's just acceleration, right? But just the magnitude of acceleration, right, without a sign on it, okay? All right, so can we go any further than that? You could, right? There's really no limit as to how many layers we could go with this. However, this is where it ceases to be relatable, right? Acceleration is something we can deal with, right? We know, and let's while we're on the subject here, let's talk about something else. If you were, for example, just put yourself in this position. Let's say you're in a car, a really nice car that rides very smoothly. Okay, you take a nap in this car, and all the shades are drawn on the car. Say it's a limousine. So you're in the back, you've drawn all the shades, and you wake up from your nap and you hear the engine. Okay? Are you moving or not? You don't know, right? What are the two things that could be, two situations you could be in and you can't tell? Could be moving in a straight line down the freeway, let's say, right? Or you could be sitting in a parking lot, right? You could be at rest with the engine idling. Does that make sense? There's no way for you to know, is there? You can't sense motion, right? You can't sense velocity. That's not something we can do. And as we talk more about this, there's some interesting discussions you can have surrounding this. For example, something I'll tell you now that we'll discuss later is that there is no preferred reference frame. That's something Einstein showed us, that there is no preferred reference frame. And so really, those two situations are exactly analogous. If you're riding along on an airplane that's traveling at 700 miles an hour, but it's traveling straight flight, and
same speed the whole time.
Same speed the whole time, right? Same elevations moving in a straight line. If you, let's say you're sitting across the aisle from somebody, if you toss a ball to your buddy across the aisle, it's exactly the same as if it were on the ground waiting to take off, right? The physics is exactly identical. You can't tell the difference. And if you can't tell the difference, the physics intuition that you're developing ought to tell you that neither one of those is fundamentally different from the other, right? It would make just as much sense from a physics perspective if you're in the plane and you're flying along. We typically would think of you moving relative to the earth at 700 miles an hour, right? From a physics perspective, it would make exactly as much sense, everything would work just as well if you considered the ground to be moving by you at 700 miles an hour. They're interchangeable, okay? Can't feel either one of those. But something could happen that you could feel in the car, and it would be unambiguous. You would know what was going on. What might that be?
Acceleration or deceleration.
Okay, acceleration or deceleration. There would be no question that whether or not that was happening. If you felt it, it's happening, right? So acceleration is different. Acceleration you can experience. You know, you can tell. Yeah, that's available to us without the need for any kind of other input. We can feel it, right, in our inner ears. So that tells us something different about acceleration. Right? Accelerated reference frames, we'll come to find out much later, are much different than what we'll call inertial reference frames later, which are just either at rest or moving at constant velocity. Same thing. At rest is constant velocity. 0, right? Okay, so We can sense acceleration. Let's talk about that. Oh, and if we were to go one step further than that, though, can you sense that? No. No, the rate of change of acceleration, the unit of that is called the slug. It's not even given a name, but nobody even knows. I mean, no one can talk about that. It's totally counterintuitive, it's not useful to us, and we don't even talk about it. Okay, but acceleration is obviously a big deal. Let's talk about acceleration now. Let's think about, let's tell some stories with a picture here, okay? I'm going to draw some kinematics motion diagrams, and these will make sense. Let's draw a pretty boring one here. Let's say if we're going to start the camera. I'm already walking, and we'll start the video camera, which has a stopwatch in it, right? So we'll start it when I get to 0. Start it right now. Okay, I'm just walking along at constant speed, stop it after 2 meters. Okay, what does that look like if I were to graph a motion diagram that is time on the horizontal axis and position on the vertical axis? What does that look like? What do you think? Yes, sir.
It's a diagonal line.
Okay, does that make sense? That would be a diagonal line. Okay, so it looks something like that, wouldn't it? If that's 2 seconds, and let's say that that's 2 meters. Does that make sense? My position is changing regularly with time, right? Okay, makes sense? What would that look like on any questions on that? Everybody see that? This is just saying that at time 0, when we start the stopwatch, right, I'm already moving in this direction, and my position, remember, we're measuring it relative to, let's say, the left-hand part of the whiteboard, right? So it's at 0, 1 second later, my position is 1 meter, another second later, it's 2 meters. Okay. What if I were to, well, I'll leave it there for a sec. Okay, so now, right underneath that, so we can line them up, let's draw a velocity time graph. What can you say about my velocity, you think, at the beginning, the middle, or the end? My instantaneous velocity, too, we're going to talk about. What do you think? What would my velocity vector look like right here? Yes, ma'am.
Faster with breathing.
Okay, I'll do it again. So I'm just going to walk through here, start, stop. So my speed was the same the whole time, okay? So what was my velocity vector? If we had to draw a velocity vector right here, what would it be? What direction would it point?
Right.
Positive direction, okay? So it's positive. What would the magnitude be? What's the magnitude of instantaneous velocity? What do you think?
0.
No.
1.
2.
It would be, well, in this case, the answer is 1. But let's go back a second. I think there's something missing from our discussion yesterday. If I'm instantaneous velocity, if I'm driving in a car and the car says I'm traveling at 60 miles an hour, what's my instantaneous speed? 60 miles an hour. What's my instantaneous velocity? 60 miles an hour in that direction, whichever direction the car is pointing, right? If I turn the car, speed stays the same. Well, the magnitude of my instantaneous velocity stays the same, but the direction changed now. Okay, does that make sense?
Mm-hmm.
So just like distance is the magnitude of position, instantaneous speed is always, by definition, it's going to be the magnitude of instantaneous velocity. It's just missing the direction, right? Okay, so one more time. My speed stayed the same the whole time. What is it if I travel 2 meters in 2 seconds? 1 meter per second. So my instantaneous velocity in this case is constant, points in the same direction, right? And so how would I graph that then? If my units are 2 seconds, and these are standard units of velocity, so meters per second, let's say.
Straight line.
Okay.
Down the line.
Good. Okay, horizontal line. Good. It's just going to look like that, isn't it? Right? Everybody agree? Okay. How about my acceleration? Do it again. Okay. What's my acceleration? What is it? Thought I heard it.
0 meters per second per second.
0. How come? Is my velocity changing?
No.
No, it's not. Okay. So you got all those. Okay. Now let's see if we can relate those in a way that's interesting. Okay, so we said that was 0. Is there a mathematical way that you think you could relate the velocity graph to the position graph? Anybody see anything there? I know you got it. Anybody else see anything there? What did we say the definition of velocity was again? The definition of velocity, instantaneous velocity, right? Or average velocity. If we take average velocity, it's just position over time, right? Instantaneous velocity is just going to be very short increments of that, which in calculus we'll come to call a derivative. We'll get there later, right? Okay. What does that look like, though? Change in x over change in time. This is the time axis, and that's the x-axis. What does that look like? What do you think? If I had a regular graph, and I did something like this, and this were the x-axis, and that were the y-axis, well, here I have change in x, which would be like change in, x is my vertical axis. In kind of a regular math setting, that might have been change in the vertical component would have been change in y divided by change in t is the horizontal variable. Here it's in x. Well, what's that?
Slope.
Slope. Ha-ha. Right? Slope is delta y over delta x. So the slope of a position time graph is equal to the value of a velocity time graph. Does that make sense? So at any instant in time, let's pick that instant right there. At that instant in time, whatever the slope is at that point, that's going to correspond to the value of the function here. Because the slope is 1 there, that means that v equals 1 there, at that point, right? Or I guess just point there, I guess. Make sense? Okay. So then what's the definition of acceleration again? Change in velocity over change in time. So Richard, what's going to be the relationship there? If acceleration equals delta v over delta t, how is the graph of the acceleration function related to the graph of the velocity function? The slope. What's the slope of this horizontal line? 0, right? Because it's flat. And what do you know? The value of the acceleration function is 0. Okay? So let's play this game again. We'll just get more complex.
Are we doing it in a nutshell?
Yeah, it is, actually. Okay, so let's try this again. So we've got position versus time. Next to that, we're going to have, or under it, velocity versus time. And under that, we've got acceleration versus time. Okay, let's try this differently. Now, this time, I'm going to walk backwards. Same thing, though. Okay? Constant speed, start, stop. What does my position graph look like? Okay, where does it, but it starts at a value of 2 at time 0, right? 2 seconds later, it's what?
0.
0, okay, and it's constant. So when I say constant speed, that's going to translate to a straight line. Agreed? Okay. So if I put some units up here, doesn't that just look like that? Okay. So then what does that tell you that the velocity time graph is going to look like? What's this slope equal to? -1. And so shouldn't the velocity time graph then just look like this? It's below the axis 1. It makes sense, right? Because my speed is 1 meter per second, but I'm going in the negative direction. So if we had just thought about it in terms of just my motion, you all would have told me my velocity vector was -1, right? My velocity was -1 meters per second. Negative because it's in that direction. Okay, what's the acceleration? 0. Again. Okay, this is getting boring. Let's pick something harder. Are you also getting a little sense for where time falls in this whole thing? Time is unique. Time is the parameter that knits together all the other kinematic quantities, right? It really makes sense for us to line up these kinematic graphs vertically because then events fall down the progression of graphs in a vertical relationship, right? This time here corresponds to that time there, corresponds to that time there, right? Okay? All right, so how am I going to draw this one now? This time I'm going to try something a little different. I'm going to start here at rest at the origin, and we're going to start the watch, and I'm going to pick up speed over 2 meters. I'm going to uniformly increase my speed. Okay? What's that going to look like on a position time graph?
Steeper.
The slope's going to increase, isn't it? Right? So does it make sense that that's going to look something like this after after 0 seconds I've traveled 0 distance. Let's say after 2 meters, 2 seconds I've traveled 2 meters, but I'm starting off slowly this time, right? After a second, I've only gone a fraction of a meter. Right, and I pick up speed, and then after 2 seconds, I've gone the full 2 meters, right? So does it make sense? It's going to do something like that. Okay, wouldn't you agree? Now think about this in terms of this is my, okay, well, we'll get to that. So what's that mean then for the velocity time graph? What's it going to do? Not the same.
It's going to be at the diagonal line.
Okay, it's going to be a diagonal line. It's going to be a diagonal line. There's a couple ways we can look at that. And this is really a good preview of what we're going to be doing in calculus. If I look at the slope of the line at any one point there, I could draw a tangent to that curve to kind of get a sense for what the slope of the curve is, right? So there it's 0. Over here it's going to be something like, it looks like it's going to be about 1, right? And over here it's going to be, well, I didn't draw this very well, but it's supposed to be about 2. Okay. I got to redraw that. So it's going to look more like this. Like that. Okay. So the slope starts there, middle it's there, it's there. If we look at this closely, we'd see that the slope is changing regular, right? So here it's going to have a value of 0. Here it's going to be, if I extrapolate that line, it's like a slope of 1. And up here it's going to be something maybe bigger. Okay, it's going to be a lot bigger than 2, actually. But let's just say to make even increments, it looks like that. Okay? Okay. As the ant crawls along this curve, his slope is increasing uniformly, and the slope of the orange graph corresponds to the value of the green graph. Does that make sense? Okay? The steeper this is sloped, the bigger the value of velocity. Okay? What's that say about acceleration?
Constant number.
Okay? Remember, acceleration is the slope of the green graph. And I shouldn't put units on here. The units might be misleading this time. Let's leave the units off because there's not going to be an obvious relationship to the units. But this is a straight positive slope line, right? The slope is constant and positive. So for acceleration, all we know, ignore the units, it's just going to look something like that, isn't it? It's going to be positive and constant. Make sense? Right? One more time. Think about this from the perspective of velocity this time. Okay? I start at rest, and I pick up velocity uniformly. My velocity is increasing steadily, like that. Okay? What's my acceleration the whole time? Well, acceleration is hard to see. But think about it this way. Instead of me walking this time, pretend I'm sliding on a frictionless surface and somebody is accelerating me. Now, we're going to study this later, but what do you think causes acceleration?
An outside force.
A force. And we'll talk about that soon, right? That's a big part of physics, but that's probably no surprise. So here's a little trick that I sometimes tell my physics students about. If you want to picture the direction of acceleration, which is sometimes hard to do, imagine an imaginary hand, invisible hand, that's pushing the object to accelerate it, right? In what direction would the hand be pushing on me if I'm accelerating in this direction? That direction, right? If the hand pushed on me with a constant force, what's going to happen to me? If there's a constant force acting on me, I'm going to accelerate. Just like when you put your foot on the gas in a car and you apply a constant force to the road, you accelerate, right? That make sense? Okay, so that really does jibe with the reality that we're seeing here. There's a constant force that's accelerating me in that direction. Okay? Now let's make this trickier even still. Okay? How much time we got? 3 minutes. Okay, we'll do one more. One more. So, position, velocity, acceleration. Okay, this time I'm going to be going pretty fast when the stopwatch starts and the camera starts. Okay, so I'm going pretty fast. I slow down and come to rest. Okay, so what's that going to look like? So my position this time is doing, I think I saw it. Okay, good. So I'm starting off with a pretty high speed, right? So the slope should be big, right? And it's going down to 0. So it's going to look like that, isn't it? Everybody agree? I'm going pretty fast, so the slope is steep in the positive direction, and I slow down and I come to rest. Okay? What about the velocity graph? What should that look like? Like that. Okay. The velocity one, it starts with a big slope here, so that means it's going to have a high value. The value of velocity is the slope of position time graph, right? And it's going to go down to 0. Okay. What's the acceleration? Yeah, the slope of this line is negative, isn't it? Right? The slope is negative. Does that make sense physically? Think about it in terms of the invisible hand. In what direction would that invisible hand be pushing on me if instead of walking I'm sliding on the ice? Yeah, the hand is pushing me this way to slow me down, isn't it? It's applying a force that way that is decelerating me. Deceleration is a four-letter word in physics. What does deceleration mean? What's that mean? What did you say? Okay, that's good. A lot of times people want to say negative acceleration. Okay, that's not a good answer. Deceleration means slowing down every time. Here's why that's not a good answer. Let's play this one in reverse. Let's say I'm going to be cruising along here at pretty high speed in the negative direction, and I slow down. I decelerated, didn't I? In what direction did the invisible hand push me? That way. So the acceleration was actually positive that time, right? Because I was moving initially in the negative direction, positive acceleration slowed me down, right? So there's a case where deceleration corresponds to a positive acceleration, right? Okay, if that didn't make complete sense, don't panic. I mean, that's first time, that's kind of a big step, but we'll talk more about it, right?
Remember, Simon's